Okay, so basically in this video we're going to be doing an example that's going to illustrate what we've discovered so far. So basically what I'm saying is we have a function f that takes a real number and maps whatever it gets to another real number, which is kind of a convention to write down to say that we have a real valued function. So I'm just explaining this at this point because there are some non-real valued functions that we won't be referring to in this course, so there has to be a distinction between that. And what I'm basically saying is we have a function f of x, and that's equals to 3x plus 2, and this is basically a straight line. We know what that is. If we try to plot it, it's not that difficult. We try to plug in a 0, we get a 2, so that's somewhere over here, and we plug in, I don't know, a 1, and we get a 5. That's somewhere along here, right? So if we were to plot a line, it would look something like this, right? Y equals 3x plus 2. So that's a line, right? And what are we expected to do in this question? Well, the first part asks us to find the average rate of change. Now we need to know the distinction, right? So let's try and find that. And the second part asks us to find what? This is the important part. It asks us to find the differential, or maybe not even the differential. Let's just not write that. Find the instantaneous rate of change. Now this is a very interesting thing to talk about at this point, right? Instantaneous. Let me just write that again. Don't want to confuse these guys at this point, right? Okay. Instantaneous rate of change. Yeah. Sorry about that. Now, but we need to define a point, right? So where this instantaneous rate of change applies to, and that point could be x equals 0. But the average rate of change needs two parameters, right? So a limit, basically. Like from this point to that point, I'm trying to find the average rate of change. I need to find the derivative of the secant line, right? So I'm going to need 2 points. So let's call those 2 points x equals 0 and x equals 1. So let's try doing the first part. We know what the line looks like, and that's right in front of us. Let's use that as an aid in this question. Okay, so for part 1, we know what the average rate of change represents, right? It's basically delta f divided by delta x. It's the rate of change of the value of y, right? Basically, y is over run, b minus a, right? And we have the 2 points over here. We have the points 1 and 0. So we know that this graph is increasing towards the right. So if we have a point 1 over here, right, and a 0 over here, it's going to be moving from left to right, right? So let's just start plugging the value for b. B in this case is 1. So f of 1 minus f of 0 divided by 1 minus 0 is going to give us the answer. But what's f of 1 and f of 0? Let's compute that. F of 1 is basically 3 times 1 plus 2. That gives us a 5. And what does f of 0 give us? Well, basically we're just going to plug in a 0. What do we get? We get a 2. So the numerator over here is going to give us 5 minus 2, and we're going to end up with 1. 3. So that's basically the average rate of change, or in other words, it's basically representing the secant line from point A to point B. What about the instantaneous rate of change? Well, we know the formula for that, right? We know that if we want to find the instantaneous rate of change, we're going to have to find the derivative at a point. And we know this looks like limit as q is trying to approach a particular number b, right, for f of q minus f of b divided by q minus p. And we know why that is, right? If you think about it for a second, we're trying to get closer and closer to the point b, because that's going to give us a tangent line, or basically a secant line in this case, which has a gradient, or which has a slope equal to the slope of the tangent line at the point b. And that's going to give us the derivative at the point b. So if we were to express this in a more concise manner, we'd say that we want to find the derivative at the point 0, and that is going to change every p value over here to z. What I meant was 0. So we change it to 0, and we get f of q, that would remain the same, and f of 0. And in the denominator, we get q minus 0. So basically, it kind of simplifies to the limit f of q minus f of 0 divided by q. Now we're going to observe some magic over here. Let's see what I mean by the word magic. So we know that we can represent f of q in general terms, right? We know if we have a function in terms of, well, anything basically, and we need to find the limit of that function, we could use the limit rules we've learned in the last module, right? So let's try to find that. We know that f of q has to represent a function, right? But we know what f of x is. We know f of equals 3x plus 2, and we can try to plug in the value of q over here to get 3q plus 2. Let's just try to put this over here and see if this expression kind of simplifies, because we're trying to find the limit, right? We're trying to find the limit as q approaches q. 0 over here. And once we do that, let's see what happens. 3q plus 2 minus f of 0. What's f of 0? Well, we calculated it above. If we have this function and we plug in a 0, we get a 2. So we get a q over here, and what we're going to do over here is try to determine what happens. And as we can observe, 3q plus 2 minus 2 is going to give us 3q divided by q. So what's happening over here? Well, if we try to use the regular limit laws over here, you guys must remember that if you're trying to find the limit at a particular point, all we need to do is plug in the value. But if we plug in a value over here, we get 3 times 0 over 0, right? That gives us a form 0 over 0. Why is that? That's an indeterminate form. We have issues with this form. What do we do? Well, if you think about it, if you refer to the previous lectures, this is not the form. Since q is getting closer and closer to the point 0, q over here is getting closer and closer to the point 0, but it never gets exactly equal to 0, which means we can simply cancel these out. So what we get essentially is the number 3. And think about this for a second. I mean, this would be cheating in a way at this point, but let's have a corner over here that refers to this, well, part in which we're trying to check if this is true. So what's the derivative? The derivative is basically how you're defining this term over here, right? But we've learned that we can calculate the derivative of particular functions using simple rules, right? We basically bring the power over here and we multiply x by that. We get 2x. And over here we can add a plus sign because it remains the same, and then 2x. The derivative of 2x turns out to be 2. So we can determine derivatives over here. Let's try to determine the derivative of y equals 3x plus 2, the function in question over here. What happens here? We know that the derivative of a constant is 0. We know that the derivative of 3x gives us 3. So we were right all along. So the method we've used to actually prove that the instantaneous rate of change is 3 is working out, and it's giving us the right answer. And if you think about it, another way to look at this problem, this might just work for linear functions, but it's perfectly fine. We have 3x plus 2, right? It's going to be a straight line. The straight line is going to have the same gradient at any point. So it's going to have the same instantaneous gradient, instantaneous rate of change, and that instantaneous rate of change is going to be equal to the average rate of change. So it's basically the same. So it kind of helps us prove what's actually going on. By the way, you guys could achieve the exact same using the f of x plus h minus f of x formula divided by h, as limit of h goes to 0, and this will represent f dash of x. And you could use this formula to find the same solution as well. I use this formula because this is something you guys experience in the web work very often. This formula is used a lot in your homeworks as well, so this might be more helpful in that way. See you guys in the next video.